Hello, everyone. My name is Joel Langford. I am a products coordinator in elemental spectroscopy at Shimadzu Scientific Instruments. And today I will be discussing using electron probe microanalysis, also known as EPMA, for measuring component distributions in joints of dissimilar materials made by friction stir spot welding. We will start with a brief outline. First, we will cover the concept of friction stir spot welding. After that, we will do two different examples of friction stir spot welding. One is of galvanized steel sheets with aluminum alloys. We will make using the SEM capabilities or the microscopy capabilities of the EPMA. We will make macroscopic observations about the weld itself, and we will make some more microscopic observations using the SEM capabilities of the EPMA of the joint interface surface. This includes observations about cracks and the intermetallic compound layer that is formed as a result of the friction stir spot welding process. We will also make elemental maps with the EPMA of the joint interface. From these maps, we will gauge the IMC layer thickness, as well as the composition or the IMC type, as well as any residual zinc within the IMC layer. We will next turn to another dissimilar material, which is that of galvanized steel with aluminum alloys. We will make SEM observations similar to the galvanized steel sheets with aluminum alloys, but in addition, we will interpret the data to do some phase analysis and some more quantitative analysis of the IMC layer itself. First, what is friction stir spot welding? Friction stir spot welding is a solid state welding method used to join two dissimilar materials by using friction heat that is generated from a rotating tool. Pictured to the right is that rotational tool. It is composed of a shoulder and a probe. In this case, what is happening is the probe is pressing into what would be an aluminum sheet. As a result of the rotation and the pressing of the tool, heat is formed from friction. This heat softens, in this case, the steel sheet, or in other words, it plasticizes the steel sheet to form what would be a welded joint. So to summarize, friction stir spot welding is comprised of a tool, which is made of a probe and a shoulder that is pressed against a joint. Heat is generated by rotation and pressure of this tool, which softens the steel sheet coating. When the coating is removed, is discharged, an IMC layer is formed. An intermetallic compound layer is formed that bonds the two materials together, that forms a weld between the two materials. The IMC layer that forms at the joint interface is typically a few micrometers thick and forms uniformly over a large area, which results in a very high joint strength bond, a very sturdy weld. In this case, as previously mentioned, the materials that we are going to bond or weld are galvanized steel or zinc-coated steel sheets with aluminum alloys. We will compare two different welds or two different joints. One is of a short pressurization time and the other is a long pressurization time. Some of the results that we will collect by probing the joint with the EPMA includes the cracking content of the IMC layer, the IMC layer thickness and composition, as well as any residual zinc within the IMC layer itself and where that residual zinc is spatially located within the joint. Pictured here is a friction stir spot weld of aluminum alloy with a sheet of galvanneal steel. The left column represents the short pressurization time, and the right column represents the long pressurization time. As you can see, a button-like indentation is made as a result of the welding process. In addition, there is a burr-like protrusion which is around the perimeter of the button. In the middle row are some optical microscope images of the welded area. This was made with a shearing machine by cutting along the welded joint itself. Pictured on the top is the aluminum alloy, and below that is the galvanneal steel sheet. You can see the button-like indentation as well as the burr-like protrusions around the perimeter of the button. To make this sample conducive for analysis by EPMA, a plastic resin was used to polish the sheared sample. In this case, at the bottom, what you can see is a backscattering electron image collected in the composition mode or the compo mode. The top of the image is the plastic resin used to polish the sample. The middle is the aluminum alloy, and the bottom is a galvanneal steel sheet. In this case, we deem this image to be macroscopic because it is on the scale of millimeters. Pictured here is, again, a macro view, a macroscopic view of the section joint that was made by shearing the weld. This is an SCM backscattering image in the compo mode. Again, you see the plastic resin at the top, the aluminum alloy in the middle, and the galvanneal steel sheet at the bottom. Using the WDS spectrometers on the EPMA, we were able to collect maps of different elements near the welded joint interface, near the weld itself. You see aluminum, silicon, iron, and zinc maps. Note that there is the formation of a button-shaped indentation, which is apparent from the compo image, as well as the formation of a joint area around the indentation parameter and a formation of burr-like protrusions around the button indentation that is apparent from the compo image. Two observations. This is for the short pressurization time. One is that not all the zinc is discharged away from the jointed interface. In addition, there is a slight change in the distribution of silicon and iron near the mixing zone of the weld. Again, this is another macroscopic view or image of the section joint. Note that approximately a 6 micrometer layer thick zinc coating was discharged away from the joint center and discharged around the periphery towards the periphery of the welded joint. However, not all the zinc was discharged as a result of the friction stir spot welding event. There still is some residual zinc within the intermetallic compound layer. The following are composition images using the compo mode, the backscattering compo mode within the EPMA. And now we have become more microscopic with a magnification of 200x. Notice the scale bar now is in 100 micrometers, denoted 100 micrometers, unlike 4 millimeters in the previous slides. At this scale, we can observe cracking within the intermetallic compound layer. The top row is for the short pressurization time, and the bottom row is for the long pressurization time. The first column is near the center of the joint. followed by what is deemed the intermediate region, which is approximately 2.4 millimeters away from the center of the joint, and the edge area, which is approximately 5 millimeters away from the joint. For the short, some observations that can be made, qualitative observations, is that for the short pressurization time, there are relatively or less cracking than compared to the long pressurization time. In addition, the IMC layer itself is thinner for the short duration time versus the long duration time. Finally, there are more cracks near the intermediate region, or the severity of the cracks is significant for the intermediate region compared to the edge and the center area, especially for the long pressurization time. To get an idea behind, or a better word, to parameterize the degree of cracking within the jointed interface, we did what was essentially a numeric quantification of cracks. So what you can see in the compo image, this is for the long pressurization time, we drew a yellow box. And that dark region is the crack itself. What we did was, in the right, what you can see is a graph of the distance from the center and the area ratio within that given yellow box. Some observations that can be made. For the short pressurization times, the cracking is insignificant compared to the long pressurization times. In addition, the cracking area ratio, or the cracking severity, or the degree of cracks within the weld, is most pronounced in the intermediate region of the weld itself. In the graph, you see long dash L, long dash R, short dash L, and short dash R in the legend. L refers to the left side, left away from the center. R refers to right away from the center. Pictured here is a more microscopic image, or a microscopic observation of the joint interface, or the region where the intermetallic compound layer is formed. Some observations. In general, for the long pressurization time, the IMC layer is much thicker relative to the short pressurization times. The degree of cracking is also higher for the long pressurization time compared to the short pressurization time. In addition, the cracking severity, or the degree of cracking, is much higher in the intermediate region, which is approximately 2.4 millimeters away from the center of the weld, as compared to the edge and the center of the weld itself. The following is mapping of the joint interface using the WDS spectrometers on the EPMA at a medium magnification of 2000x. This is for only the short pressurization time and not the long. The leftmost image is the compo image, followed by an overlay of 3 different elements: aluminum, iron, zinc. In the middle is the intermetallic compound layer. To the right is aluminum K-alpha map, iron K-alpha map, and zinc K-alpha map. Note that the IMC layer is thickest at the center area compared to the edge area. In addition, there is more residual zinc, with an average of 3.51 versus 4.08 within the field of view at the edge area versus the short, versus the center of the weld. Or to put it in other terms, there was more zinc discharged away from the center of the weld versus the edge of the weld. The center of the weld, or the center of the joint, has less residual zinc compared to the edge area. From the maps, we can gauge the IMC layer thickness as well as the zinc concentration at the IMC layer, or the joint interface. For the long pressurization times, the thickness of the IMC layer is overall higher or thicker compared to the short pressurization time. As you get closer to the center of the weld, for both the long and the short pressurization times, the thickness increases, or in other words, the thickness of the IMC layer is at its maximum from the center, at the center of the weld. Note that for the long duration time, the zinc weight percent is higher as compared to the short duration time, meaning that comparatively speaking, not as much zinc was discharged in the long welding process as compared to the short pressurization welding process. To summarize the IMC layer, for the high pressurization time, the ratio of cracks is higher, the IMC layer thickness is thicker, and the residual zinc is higher for the high pressurization time compared to the short pressurization time. This leads to a tensile shear strength that is low. We corroborated this hypothesis, or confirmed this hypothesis, by using a precision universal testing machine to measure the tensile shear strength of the joint. And as we expected, for a long pressurization time, the tensile shear strength is lower, or it's not as strong as compared to the short pressurization time. In other words, the bond strength, or the weld strength, the joint strength, is higher on average for the short pressurization time versus the long pressurization time. We next turn to another weld made from a different set of two dissimilar materials. In this case, it's an aluminum alloy welded to galvanized steel. The top row is a macroscopic, or relatively a medium magnification image at the scale of 100 micrometers using the compo mode on the EPMA of the region where the IMC is formed. The yellow boxes are a magnification that is represented by the second row of the PowerPoint slide. Again, at the top is the aluminum alloy, the bottom is the steel sheet, and in the center you can see the IMC layer that is formed as a result of the welding process. Some observations regarding the IMC of this material, of these two jointed materials. The IMC is thickest at the center compared to the edge and the intermediate region. Also note that there is a marbling pattern that is particularly apparent at the edge of the compo image. This is from zinc diffusing into the aluminum alloy as a result of the friction stir spot welding process. One other note, is that cracking is more apparent at the edge area versus the intermediate and center area. The following are elemental maps collected with the WDS spectrometers on the EPMA at a magnification of 5000x. The first column is the compo image collected from the backscattering electron detector on the EPMA. The following columns after that are elemental maps: aluminum, silicon, iron, and zinc. The top row is the center area, followed by the middle row is the intermediate region, and the bottom is the edge area. Some observations. The IMC layer is thickest at the center of the weld and gets incrementally thinner as you go out to the edge area. One other note is that it is apparent that 3 different layers are composed of the IMC itself. In the center area, the IMC itself is the thickest, followed by thinning out towards the edge area. Most of the zinc in the center area has been discharged to the periphery of the weld. Notice that in the edge area, the zinc map is much higher in intensity as compared to the zinc map in the center area. Many cracks are formed in the edge area due to inadequate zinc being discharged around the edge area, which results in the formation of a thinner IMC layer and many more cracks. Quantitative mapping analysis of the IMC layer at the microscale at a magnification of 20,000x. The following is the compo image, as well as 4 quantitative WDS maps of 4 different elements: aluminum, iron, silicon, and zinc. Note that at the center area, the IMC layer is formed from 3 distinct layers that have a thickness of approximately 0.4 micrometers, 1.7 micrometers, and 0.7 micrometers. There is residual zinc present even at the center of the weld. Note that also the silicon concentration is increased in the IMC layer relative to the aluminum and the galvanized steel alloy. Phase analysis of the IMC layer. From the WDS maps of iron, aluminum, and silicon within the IMC layer, 2-dimensional scatter plots were made. One of them was where aluminum is on the x-axis and iron is on the y-axis, while the other is where aluminum is on the x-axis and silicon is on the y-axis. Filters were applied to identify compounds and where they were present with respect to the depth of the IMC layer. For the compound Fe2Al5, the eta phase, that compound was most present near the first IMC layer that is closest to the steel sheet, followed by the theta phase, FeAl3. Note that in Fe2Al5, the iron atomic ratio is 40% versus the FeAl3 theta phase, theta compound, where the iron atomic ratio is 33%. The aluminum silicon scatter plot was used to fill out the rest of the regions in the IMC layer. Quantitative analysis of the IMC layers. Pictured as a compo image of the IMC region in the center of the joint, with 3 different layers demarcated: IMC layer A, IMC layer B, IMC layer C. It is expected that the most concentrated iron aluminum intermetallic compounds will be located next to the steel sheet in IMC layer A. In this case, it would be the eta phase, Fe2Al5. This table here is of different iron aluminum intermetallic compounds. The first column notes the empirical formula. The second is the iron weight percent. In brackets is the atomic weight percent. And then the third row is for aluminum. Note that the most concentrated of iron weight percent phases is Fe3Al. It is expected that layer A is principally composed of Fe2Al5, the eta phase, as was shown in the scatter plot diagrams in the previous slide. In the middle, below is a table of the quantitative elemental analysis for the intermetallic compound layer in the center of the joint. IMC layer A is, for example, composed of 45.3 weight percent iron, 51.2% aluminum, and so forth. As you get farther away and closer to the aluminum alloy, the iron content decreases while the aluminum content increases. Also note that there is a non-negligible amount of zinc within the intermetallic compound layer, even at the center of the weld. The silicon content is most concentrated at IMC layer C. In summary, for the long pressurization time relative to the short pressurization time, the residual zinc content was higher, the IMC layer thickness was thicker, and the cracking quantity was higher. This led to a lower joint strength, as was confirmed with universal testing frame measurements. An IMC layer was observed using the EPMA 8050G and including the IMC layer thickness as well as the IMC layer composition was all measured with the EPMA. To summarize, the EPMA enables elemental distribution analysis from the macro to the micro scale. Thank you for your attention.
Excellence in science. Shimadzu.